Okay, good afternoon, everybody. Welcome to the TPA seminar. Today, we are pleased to have Jim Fuller with us. Jim did his master's and PhD in physics at Cornell University, and then continuing as a postdoc at the Kepler Institute for Theoretical Physics at UC Santa Barbara and at Caltech, and then becoming an assistant professor of astronomy at Caltech in 2017. Jim is a theorist working on wave propagation in stars and planets, with applications that include binary evolution, tidal interactions, and rotational profiles of supernova progenitors, among other things. And today he'll tell us about the role of gravity waves in angular momentum transport and mass loss in stars. So welcome, Jim.
Okay, thank you, Rodrigo. And thanks everybody for coming. Sorry I can't meet you in person. I'd really love to visit University of Alberta at some point, but we'll have to settle for a remote talk. For those of you expecting to hear about gravitational waves, I hope you're not too disappointed. You're going to learn for this entire hour about fluid dynamics and gravity waves, but they have some really important applications in astrophysics. And as we'll see, actually, they even relate to observations of gravitational waves. So there's lots of good physics in this talk. So gravity waves are basically buoyancy waves. So they're waves that propagate in stably stratified regions. I'll come back to that slide. They're waves that propagate in stably stratified regions of stars and planets and really almost any kind of fluid. A classic example is the interior of the sun. So the sun has a convective envelope. This is a snapshot from a simulation by Lucy Alfan. See the convection and the exterior of the sun, and interior to that, there's a radiative zone that has a stabilizing buoyancy force, and that allows gravity waves to propagate in that part of the star. And so that's what all this small length scale structure is. Those are gravity waves propagating in the interior. On the right, we have a simulation. This is a simulation of, oh, it looks like it doesn't work. For some reason, the movies in my slides got cut out. But what you see here is a simulation of convection in a massive star in this case. And so you see the turbulent convection here, and above and below the convective layer, you see gravity waves. So again, that's these waves with short radial wavelengths, but pretty long horizontal wavelengths here. So those gravity waves, they sort of show up everywhere. So we see them in stars and planets, but also things like accretion disks and galaxy clusters. So they're really important in many different applications. And one of the reasons they're so important is that they carry information. So we can, in many cases, we can see stars pulsating in gravity waves. We can observe that directly. And they carry information about the interior of the star or the planet they're propagating in, because those waves propagate through the whole interior. So that allows us to do some really unique asteroseismology, which I'll spend most of the talk discussing. But those waves also carry energy and angular momentum. And in some cases, they can actually carry so much that they have a really profound impact on the evolution of a star. So we'll see some interesting applications where the wave power actually makes a big difference. But I'm going to start by talking about the interaction of gravity waves and magnetic fields in a topic that I like to call Magneto astroseismology, which is a bit of a mouthful. But basically what we're going to do here is we're going to learn how to use astroseismology to measure magnetic fields inside of stars. And this is a really important subject because we know almost nothing about magnetic fields inside of stars. We know they have to be there, we know they're important, but it's really hard to measure them. So there hasn't been a lot of work on it. And what we're going to see is we can actually use gravity waves to identify strong magnetic fields and potentially even measure their field strengths. So this is work done with several people, but I really want to highlight the contributions of Matteo Cantiello, who helped do a lot of the work I'm going to show. And a lot of the data you're going to see is from Dennis Stello, who is an observer who's done a lot of really great astroseismology observations. So let's start with the basics of astroseismology. This field has really been revolutionized over the last decade or so largely because of data from space-based telescopes like the Kepler telescope. So all that telescope did is it stared at about 100,000 stars, and it just measured their brightness very accurately. So this is an example of a light curve from Kepler. You see kind of longer time scale variation. That's due to spots rotating across the surface of the star. But there's also some short time scale variability you can't really see. It looks like noise here, but that's actually stellar pulsations. So when you take a Fourier transform of a light curve like this, then what looks like noise actually breaks up into a very clean spectrum of peaks. And each one of these peaks is at a discrete frequency. Typically, those periods are of order minutes or hours for stars. And each one of these peaks corresponds to a discrete oscillation mode of the star. And that allows us to do asteroseismology. So it's a little hard to see, but each one of these peaks is labeled by a number. That number corresponds to the spherical harmonic index of the pulsation that's producing that signature in the light curve. So the highest peaks here, those are labeled 1. Those are L equal 1 or dipole modes. So if you remember from quantum mechanics, you can solve for wave functions of, say, a hydrogen atom, and all the angular wave functions are spherical harmonics. It's the same thing in stars because they're to first order spherically symmetric. And so the oscillation modes are basically spherical harmonics. So there's radial pulsations where the star pulsates in and out. There are dipole modes where basically the star moves side to side. And then there are quadrupole oscillations where the star kind of squishes up and down, and then higher order modes as well. So these dipole modes are going to turn out to be crucial. But what you see from a spectrum like this is that there's a very regular structure here. You see this kind of doublet here. This is composed of a quadrupole oscillation right next to the radial oscillation. And then about halfway in between, you see that pattern repeat. Then about halfway in between those doublets, there's a singlet, which is just the dipole oscillation mode. Okay, so that's kind of a simplified power spectrum that we see in a lot of stars. And there's two very important things that we measure from a power spectrum like this. The first is that this whole power spectrum is centered around a characteristic frequency, which is called nu max. And that's basically determined by what excites the pulsations, which for many stars like the sun or red giants is basically just convection in the outer layers of the star. So nu max is more or less the convective turnover frequency at the outer edge of the star. That excites pulsations of about the same frequency. So it turns out that that frequency is proportional to the surface gravity of the star. So if we measure nu max, we get a good measurement of the surface gravity of the star, just from the light curve, which is really great. And the other thing you'll see is this pattern of peaks repeats, and each repetition is spaced by a frequency spacing called delta nu, or the large frequency spacing. And what's going on here is that each one of these successive modes, every one of these peaks labeled 1 is a dipole mode, but they have successively higher radial orders inside of the star. So going from one peak to the next, you're just increasing the number of nodes in your wave function inside of the star as a function of radius by 1 every time. So that's called the radial order. And this large frequency spacing, turns out, is basically proportional to the sound speed crossing time throughout the star. And that, it turns out, just scales with the square root of the density of the star. So if you measure this large frequency spacing, you measure the density of the star. If you combine that with the measurement of surface gravity, you can then solve for both the mass and the radius of the star. So this has been one of the revolutions of asteroseismology, is that we can, just from photometry, just from measuring the brightness of a star, you can accurately measure its mass and radius. So this has allowed mass and radius measurements for thousands of stars. And that's really revolutionized the field. But we can do even more interesting things, which I'm going to get to. But I want to focus primarily on red giant stars. So these are stars similar to the sun, except similar in mass, but they're more evolved. So they've burned all the hydrogen in their cores. and then they start burning hydrogen in a shell. So they have a helium core surrounded by a hydrogen burning shell, and then the whole surface of the star expands. So the star inflates into a red giant. And most of the star is composed of this convective envelope of the red giant. And the gravity waves, they only propagate inside this interior region. But it turns out we can see those waves due to their coupling with acoustic waves in the envelope of the star. So this is the kind of structure of stars that I'm going to be focusing on. So to help understand what we see in those stars, it's useful to talk about a propagation diagram. So what I'm plotting here are two different important frequencies as a function of radius within a star. And those are going to help us interpret the pulsations that we see at the surface of the star. So the first frequency that's really important here is this blue solid line. This is called the Brunt-Väisälä frequency, or the buoyancy frequency. This basically measures the strength of the buoyancy restoring force, which determines the properties of gravity waves. So what you see here is that this buoyancy frequency it's basically 0 in the surface layers of the star where it's convective. And in the core, it gets very large, especially right here, there's this spike. That's right at the hydrogen burning shell of this star. So that's where you get a really sharp density gradient and hence a very large buoyancy force. And the other frequency that's really important is this red dashed line. That's called the Lamb frequency. That's basically a sound speed divided by a radius. So that tells us how acoustic waves propagate. And if you solve for the dispersion relation of fluid waves propagating through the star, you get this kind of complicated expression here. But what's important is that in the limit of high frequency, so in other words, if the wave frequency is larger than both the Brunt and the Lamb frequencies, like it is in this red region of this plot, that's where the dispersion relation basically just reduces to that of sound waves, which I'm sure you've all seen the sound wave dispersion relation. Or it's also basically the same as electromagnetic waves. You just replace the sound speed with the speed of light. So those are acoustic waves, and that's the pulsations we see in these stars. They behave as acoustic waves or sound waves at the surface of the star. But in the interior, that same frequency is smaller than both the Brunt and the Lamb frequencies. And in that regime, this dispersion relation reduces to that of internal gravity waves. And what's important here is that the wave number is proportional to the Brunt-Väisälä frequency. So what that means is at this spike in Brunt-Väisälä frequency, these waves have very, very short wavelengths. And that's actually going to be really important for understanding why these waves are good magnetic field detectors. So we'll come to that in a second, but just to give you a picture of how these waves propagate, what I'm going to show here, this is basically if you followed one ray, so if you thought of like a wave packet traveling through the star, it would take a path something like this, where it moves nearly radial at the surface where it's a sound wave. And in the core of the star where it's a gravity wave, it propagates in this tightly wrapped spiral pattern. So it makes these nice kind of spirograph diagrams. And what this means is that the pulsations we see at the surface, they're composed of waves that actually spend most of their time propagating through this radiative core of the star. So even though that core is very small, the wave spends most of its time propagating there. And so we get a lot of information about that part of the star by observing the pulsations at the surface. So that's really cool. And that allows us to really understand the cores of these stars very well. So to go into that, I'm going to show you a more detailed power spectrum of a pulsating red giant star. So this is similar to the power spectrum I showed you before. Each one of these peaks is one of the oscillation modes of the star. But you see a lot more structure here because this is for a red giant star. So I'll go through some of this, but what I want you to focus on, let's start by looking at this set of peaks right here. These are labeled 1. That's because they are a group of dipole oscillation modes. And you see that it's split into a triplet. And the reason for that splitting is that for an L equal 1 spherical harmonic, you can have M equal -1, M equal 0, or M equal 1. right? Those are the azimuthal numbers. And because stars rotate, the m=1 modes get Doppler shifted to slightly higher frequency, and vice versa for the retrograde modes. And so what you see here is a rotational splitting. And so this actually tells us the rotation rate of the inner layers of the star. So I'm going to come back to that in a bit. But the other thing that we see here is we see this triplet here, and we see another triplet here. And then it's a little harder to see, but there's another group here and another group here. And so those multiplets are split by what's called a period spacing. And it turns out that that tells us about the core structure of the star. So that's what we see in a lot of red giants. But it turns out that there are some red giants where we see something very different. And this was a mystery several years ago that came up. So again, on the right, I'm showing you some power spectra of a couple different red giants. These are two different stars. At the surface, they would look almost identical, but their power spectra look very different. And what you notice here is that this star has a lot of power in these dipole oscillation modes. Okay, so you see these, the dipole oscillation modes are the red ones, the radial modes are the black ones, and then the quadrupole modes are the blue ones. So usually we see the most power on the radial and the dipole modes, but there are some stars where you still see the radial modes, but you just don't see the dipole modes. And that's super weird because you'd think if a star could pulsate in one kind of mode, it should be able to pulsate in other kinds of modes. So this is the mystery of the suppressed dipole modes. But one hint that was telling us about what might be happening very early on is that it's these dipole modes you see that have more structure here, because those are the modes that really spend the most time propagating in the core of the star. So immediately we had a hunch that whatever's happening to these stars, it has something to do with what's going on inside of their cores, because that is where you can really affect the dipole modes. So there must be something different about their cores. And what's interesting is that you see this effect in really a large fraction, about 20% of red giants. So what's plotted here are the visibilities or the amplitudes of those dipole modes in many different stars. So each one of these dots is a different star where Dennis Stello measured the power in the dipole mode as a function of nu max. So you see two very different groups of stars here. They're the ones with normal power up here, and they're the ones with much less power in their dipole modes down here. It's about 20% of stars are in the second branch. So whatever's going on was pretty common. So like I said, it's the dipole modes that really tell you about the core of the star. But you can think of the star as basically being like a square well, like a problem you've done in quantum mechanics, except there's two square wells. So there's like an outer square well due to where the waves propagate as acoustic waves. Then there's an inner square well where the waves propagate as gravity waves. And they're separated by an evanescent region. So what we did is just a very simple calculation, which is if you think about a wave trapped in this square well and it's leaking power into this well, you can calculate pretty easily the rate at which it's losing energy. It's basically just determined by the thickness of this evanescent region. So it's basically just the energy in this cavity multiplied by a fraction of wave energy that leaks through this boundary every time the wave propagates back and forth, so every wave crossing time. So that's the rate at which this mode would lose energy. And that allows you to then calculate the amplitude that such a mode would have relative to a normal mode where the power that leaks into the core is able to come back out. And so you can easily compare this ratio of visibilities to the data. And what you get is this red dashed line. So this, you can see, matches the data very nicely. And what's even better is there's no free parameters. This is, this red line is predicted completely by, if you have a stellar model, then you can just calculate this line basically exactly. So it's very clear that whatever's going on inside of these stars, it's due to basically pulsations in the envelope that are leaking energy into gravity waves that are going into the core, and for some reason the gravity waves aren't coming back out. So in this upper branch of stars, the gravity waves are able to propagate to the core and come back out, but not in this lower branch. So what's going on in these stars? Well, you can probably guess that what we think is happening is that there's a strong magnetic field in the cores of these stars. And that actually disrupts the gravity waves due to an effect we like to call the magnetic greenhouse effect. So what we're going to see is that when the waves hit this magnetic field, they basically convert into a third type of wave called alpha waves, which are basically just magnetic waves. And it turns out those then get stuck in the core of the star, so you don't see those pulsations at the surface. So to understand that, what I've written down here is basically a dispersion relation for magnetogravity waves. So this includes both buoyancy forces and magnetic tension forces. And the basic, so what K squared, this is the wave number here of the wave. And there's a bunch of terms here, which I don't want to explain all of them. But what you see is that there's this term in the square root, and that's equal to 1 minus this big nasty number that is proportional to the alpha and speed squared. So basically it's proportional to the magnetic field strength squared. So as you go to higher and higher magnetic field strengths, what happens is eventually this term becomes larger than 1. So this term under the square root becomes negative. And so that means that this wave number becomes complex. And that means that the waves become evanescent. So basically the gravity waves go in, and eventually the magnetic field becomes strong enough that the waves can't propagate anymore. Basically, there are magnetic tension forces that are too strong to allow the wave to propagate anymore. And you can think of that as, you can think of magnetic fields as like springs that are embedded in the plasma. So to demonstrate that, I have a wire here. It might be a little hard to see, but you can think of the magnetic field as being like a wire with tension. And so it takes some energy to bend it back and forth. And what gravity waves do, because they have short radial wavelengths and large horizontal velocities, they take a radial magnetic field and they really try to bend it back and forth. And if the magnetic field is strong enough, you can think of this wire as becoming really stiff. And so then the waves can't bend it anymore. And so you can calculate pretty simply about the magnetic field strength you need in order to prevent the wave propagation. And it just boils down to this number, which just depends on the wave frequency divided by the Brunt-Väisälä frequency. So what happens is, as the wave propagates into the core of the star, where the Brunt-Väisälä frequency is really large, then a magnetic field of sufficient strength will disrupt its propagation. That also occurs when the alpha and speed's basically the same as the group speed of the waves. So that's what we think is happening. By the way, this magnetic field strength that you need in a typical red giant star is something like 10 to the 5 Gauss. So that is a pretty large field strength, but it's actually a smaller magnetic flux than we see in magnetic A stars or magnetic white dwarfs or other kinds of magnetic stars. So it's actually not, it's a very reasonable field strength that we think could exist inside of stars. And so we think it does exist in a lot of these red giants. So we still don't fully understand what happens when the wave hits the magnetic field in a realistic situation where you have kind of a complicated magnetic topology. But at least in this simplified case, this is some really nice work by Daniel Equanet. He did a 2D simulation of gravity waves that in the simulation what happens is he excites waves up here, they go down, they hit the magnetic field, and then what happens is they go back up in basically these alpha waves, and at a certain height, you see that they develop extremely small scale structure. And so what happens is the waves in the simulation, they just dissipate because there's a finite viscosity. And something like that would probably happen in a real star as well. That basically what happens is the waves, they go down, they convert into these alpha waves that then develop very short wavelengths and are dissipated. So I like to call that the magnetic mirror effect. But the basic result is that any gravity waves that come into the core of the star will then get converted to alpha waves, which will then dissipate inside of the core of the star. And so that will reduce the pulsation amplitude that you see at the surface of the star. So that's what we think is going on. I think we don't totally understand this for more complicated magnetic topologies. It's possible that some power actually does get out, and Cleo Loy has done some recent work suggesting that even for large magnetic field strengths, you still get a little bit of power out. And that may be seen in stars if you look very carefully in their pulsation spectra. Even in stars that have these low amplitude dipole oscillations, there still looks to be a little bit of structure, which suggests that maybe a little bit of the wave power actually is getting back out of the core. So that's ongoing research, but I think almost certainly what's going on in these stars is that there is a strong magnetic field in their core. And what's really interesting is if you look at this incidence of strong magnetic fields as a function of stellar mass, you see this very interesting trend that, so what I'm plotting here is the fraction of stars that show this dipole mode suppression. In other words, the fraction of stars that we think have strong magnetic fields in their cores. I'm plotting that as a function of stellar mass. And what you see is that in one solar mass red giants, like the descendants of the sun, you basically never see these strong magnetic fields. So we think the sun, and when it becomes the red giant, probably does not have a strong magnetic field in its core. But these higher mass stars, above about 1.5 solar masses, you see this in about half of stars. So it's very common in those stars. And what's different about these types of stars is that stars like the sun, they have a radiative core on the main sequence. But these more massive stars, they actually have a convective core. So what that means is they have convection right at their centers. And that convection can create a magnetic dynamo. So just like we see a magnetic dynamo at the surface layers of the sun where there's convection, we think there can also be a magnetic dynamo in the cores of these stars. And Kyle Augustin has done some really nice MHD simulations of that process where he does see very large magnetic fields develop. And what this is telling us is that those magnetic fields that develop during the main sequence lifetime of the star, they're probably able to survive at least about half the time and remain as strong magnetic fields even after the convection turns off. Those magnetic fields apparently become embedded in the core of the star where they can suppress the oscillations of the red giants. So I like to call those skeleton fields because they're basically the leftovers of this magnetic dynamo that happened in the main sequence evolution of these stars. So that's our interpretation for what's going on. So again, all these stars with normal oscillation modes, those do not have strong magnetic fields, but the ones with suppressed oscillations, they have these magnetic fields that we think were built by a convective dynamo. So some of the implications of this are that basically these strong magnetic fields can probably survive into later phases of stellar evolution. And so one of the possible implications is that magnetic fields created by convection during any phase, any lifetime, any part of a star's life can survive all the way potentially until the star forms a compact remnant. So it's possible that some magnetic white dwarfs that exhibit strong magnetic fields at their surfaces, those magnetic fields may have actually been built by this process. We don't totally know yet. And similarly, magnetic neutron stars, which are basically just coming from the cores of massive stars, so those magnetars can have field strengths of 10 to the 14 or 10 to the 15 Gauss. And what's really interesting is if you estimate the expected magnetic flux from a dynamo like this that happens in the core of a main sequence massive star, if that magnetic flux is conserved all the way into a neutron star, then the expected magnetic field that you get is of order 10 to the 14 or 10 to the 15 Gauss. So it might be that a lot of the magnetars we see are actually, their fields may have actually come from dynamos when the star is on the main sequence, and those magnetic fields were able to survive all the way into the neutron star phase. We don't know that for sure, but I think that's a real possibility. So we'll need to do more work on different kinds of stars to try to figure out if that's what's going on. Okay, so next I'm going to transition into rotation, magnetic fields in rotation, and compact objects. And then I'll talk a little bit about effects of gravity waves and how they can actually potentially create outbursts in stars and massive stars that go supernova. But I wanted to pause here and see if there's any questions about this portion of the talk.
If people have questions, they can raise their hand on Zoom. So actually, I have a question, and I don't want to cut off the flow of the talk, but basically you said that these gravity waves can couple to event waves, and I was wondering, does the presence of the magnetic field in the core still does not affect the condition that compressional modes are suppressed? I'm thinking magnetosonic waves, those are also suppressed. It's only the incompressible.
Yeah, that's a good question. So in order for magnetosonic waves to really feel the magnetic field, you need the magnetic pressure to be comparable to the gas pressure. And that requires an enormous magnetic field strength in the cores of these stars because they're really dense, they have very large gas pressures. So the kinds of magnetic fields I'm talking about are many orders of magnitude below the gas pressure. So they wouldn't affect the magnetosonic waves, but they will affect the magnetogravity waves.
Yeah, thanks. Any more questions for Jim? All right, sounds like you can keep going.
Yeah, if you think of any, we can talk about it at the end. So the next thing I want to talk about is the spin of stellar cores. This is an important question because, sort of like magnetic fields, we don't really understand how stars rotate, and in particular how the inside of stars rotate. And this is really important because the angular momentum contained in the core of a star, that's what's going to determine the rotation rate of like a neutron star and a pulsar that forms from the core of a massive star, or the rotation rate of a black hole that forms from the core of a very massive star. So that rotation rate is going to depend on how much angular momentum is contained in the core, and that in turn depends on coupling between different layers of the star. So typically as stars evolve, their outer layers expand and they tend to spin down. The inner layers contract and tend to spin up if they conserve angular momentum. That means there's a lot of shear, and so if there's any angular momentum transport between this rapidly rotating core and the slowly rotating envelope, that will spin down the core, it will sap the angular momentum from the core, and so you'll be left with a compact object that's more slowly rotating. But we don't fully understand the physics of what couples these layers. In other words, the frictional processes that are occurring inside of the star. And we'll see that I think it's related to magnetic fields again, but also again, it's gravity waves to the rescue in terms of making progress on this problem, because like I said before, with this astroseismic data, we can actually measure the rotation rates of the inside of a star. So this is that same plot I showed you before where you see 3 different oscillation modes that are split by the rotation rate of the star. And what you'll notice here is that this group of 3 modes is split by a smaller amount than this group of 3 modes right here. And the reason is that this mode is largely confined to the envelope of the star, to the surface layers. And this mode, it turns out, is largely confined to the inner layers of the star. So the fact that it's split, rotationally split by a larger amount, means that the inner layers of this star are actually rotating faster than the outer layers. So we can measure the rotation rates of the cores of these stars using these gravity waves. So that's what Benoit Moser has done, and there's some updates to this figure, but they're more or less the same, that the rotation periods of, again, these are low mass stars, so these are like 1 or 2 solar masses. So the rotation periods are something like 10 or 20 days when they're going up the red giant branch. So that number may not mean much to you, so it helps to compare it to what we expected to see. So what I've plotted here is the rotation period of the core of the star as a function of its radius. So as stars evolve up the red giant branch, they get bigger and bigger, so they move to the right on this plot. So if the star rotated as a rigid object, because it's getting much larger, its moment of inertia increases, and so it would have to rotate slower and slower. So if the star rotated as a rigid object, we'd expect all the measurements, which are these black points, we'd expect them to lie on this solid, on this black line. And that's clearly not what's happening. So what this means is that the cores of these stars are rotating quite a bit faster than the surfaces, about a factor of 10 times faster. On the other hand, if there was no angular momentum transport inside of the star, then what would happen is the core would contract and it would spin up and it would lie down here on this green line. And then we'd expect the cores of these stars to rotate about 1,000 times faster than what we actually see. So clearly there is a lot of angular momentum transport that's causing the cores of the stars to lose most of their angular momentum and spin down, but not enough to make the star actually rigidly rotating. So we don't understand this very well, but I think magnetic fields are the most likely answer for what is actually causing this coupling and transporting angular momentum. And one of the ways they probably do this is through a mechanism called the Taylor-Sproit dynamo. So the idea here is that if you have a weak magnetic field inside of a star, so I'm going to use my wire to represent a magnetic field again. If the star is differentially rotating, so imagine the surface layers up here are rotating faster than the inner layer, or well, let's say the surface layers are rotating slower. So then these inner layers are going to rotate faster, and basically what that's going to do is it's going to stretch the field horizontally. So in other words, it's going to wrap up the magnetic field into loops. And that amplifies the magnetic field. So basically it gains a little energy from the differential rotation. And eventually the magnetic field gets large enough that it becomes unstable. And the first instability that we think happens is called this Taylor instability. And that's similar to what happens if you take like a slinky and you try to twist it. It's going to tend to buckle and push out some loops to the side. And so basically a magnetic field will do a similar thing where the magnetic loops buckle to the side via the Taylor instability once their field strength gets large enough. And so then what happens, so that's the linear instability. What actually happens as an outcome of this process is not well understood. It's a very complicated MHD instability that somehow saturates, but we don't really understand it. So I have a long paper discussing what might happen. But to first order, what we think happens is that there are nonlinear damping processes that basically prevent this instability from growing too large. And so that means you basically, when you slip this field sideways, it regenerates the radial magnetic field. And the larger the instability the larger in amplitude the instability grows, the larger radial magnetic field you generate. And that means you have a larger Maxwell stress that can transport angular momentum in the star. So how this instability saturates will basically affect how much angular momentum transport you get within the star. And then the classic paper by Hank Sproit, he proposes one mechanism for how this instability saturates, and that gives you an effective viscosity of a magnetic field that scales in this way. And what's important here is it scales like the rotation rate of the star divided by the Brunt-Väisälä frequency to the 4th power. So it's this very strong scaling. And this number is very small in stellar interiors. So that means you get a very weak viscosity from that mechanism. We believe the damping is a little weaker. And so that means you get stronger magnetic fields, and that means you get a larger viscosity that only scales with the square of this number, according to our work. So that means you get more angular momentum transport by these magnetic fields. So what we can do is we can take a prescription like this and we can put it in a stellar evolution code, and we can model the rotation rate of the inside of the star, and we can compare it to data. So that's what's shown here. What I'm plotting here is the rotation period of the core of the star as a function of time. And the observations are these colored ovals. And our new model is this red line, which you can see matches the asteroseismic data pretty well in the red giant phase, in the clump phase, which is where the star is doing helium burning in its core, and then also in the white dwarf phase. It seems to match all those phases pretty well. And there's basically only one parameter here. It's like a saturation parameter alpha, which we expect to be of order 1. So I'd say this all looks pretty good. And it certainly does better than the prior prediction from the Taylor-Sproit dynamo, which is this black line, which is predicting rotation rates too fast by a factor of 20 or so. So I think this is certainly a step forward in our understanding. And to first order, it can explain what we see in low mass stars. So then the question is, what happens in high mass stars? So we've put in the basically same physics into models of high mass stars. So there we don't have the astroseismic data to calibrate this. But if the same physics is happening in high mass stars, then most of the core's angular momentum will be extracted over the lifetime of the star. So what's plotted here, this is some of our high mass star models, where what I'm plotting here is the specific angular momentum of the core of the star as a function of time. So this is the main sequence part of the star's evolution over here. And then after the main sequence, what happens is the core contracts and tries to spin up, the envelope expands and tries to spin down. And so that's when you generate the shear that creates the Taylor instability that causes a lot of angular momentum transport. And so at that phase, the core, according to these models, loses 90% or 99% of its angular momentum. And by the time the core collapses into a neutron star, so that's at the end of these red lines here, then its angular momentum has been reduced by a factor of 100 or 1,000 or so. So according to these models, these cores lose most of their angular momentum. And if you translate that into a rotation period of a neutron star, sorry, my mouse is on the fritz here, then the expected rotation periods are of order 100 or 200 milliseconds. So this is actually pretty similar to what's observed for young neutron stars, for young pulsars. It's a little bit on the slow end, but there are other processes that actually might spin up the stars a little bit during the explosion. Some people have been doing some really nice work on that. But I think it's likely that most of the angular momentum is removed by these magnetic processes throughout the evolution of the star. So that equates to pretty slow neutron star rotation rates in most cases. And the story is similar for massive stars that form black holes. So here what I'm plotting, these are very similar models, but now I'm plotting the specific angular momentum of the helium core of the star. And so what happens is the star evolves off the main sequence, and then it loses almost all of its angular momentum due to these processes. So most of these models end with very low angular momentum. These green and yellow ones have a lot higher angular momentum, so I'll come back to those in a second. These are models that probably give us rapidly rotating black holes. But in most cases, we think you probably get pretty slowly rotating black holes due to this process. So if we then translate those core rotation rates into dimensionless spins of a black hole, assuming that the angular momentum of that helium core is conserved and that the helium core collapses into a black hole, then you basically, for single stars, you get these black points. So those are all very slowly rotating. So this is spin of the black hole as a function of the mass of the black hole, basically. And the great thing now is that we can actually test some of these predictions with gravitational wave data. So all these points are mergers of black holes observed by LIGO. And so what's plotted there is the chirp mass and the chi-f. So this is the aligned component of the spin that we can measure really well, or at least measure pretty well. And what we see is that there's pretty big uncertainties for a lot of these, but in most cases, this measured spin is consistent with zero, or it's very close to zero. There's not many black holes that have very large rotation rates, or very large chi-f values. So that suggests that most black holes are indeed slowly rotating when they merge. Now, there are a few events that do appear to have much more rapid rotation. And those, I think, are consistent with some of these other processes that can happen, especially this green point or this yellow point. So those are models where basically the core gets a reinfusion of angular momentum late in its life. So the green is a model where it's in a close binary. Remember, all these observed events are binary black holes. So they have to be, you have to have, before the star forms a black hole, it's going to be in a close binary, in many cases with another black hole. And that means it can get tidally spun up, and that can basically add a bunch of angular momentum back into the star and allow it to be rapidly rotating when it collapses. This yellow point is a different kind of evolution that we're not sure if it happens or not, but it's called the homogeneous evolution. That's basically what happens there is the whole star burns itself into helium, and so the whole star collapses into the black hole. There's nowhere for the angular momentum to go, so it basically, most of it gets conserved, and so all the way from the main sequence. So that can also give you rapidly rotating black holes. So I think that's what's happening with these higher spin measurements from LIGO. But we're going to need more data to really statistically test these predictions. So I'm looking forward to that over the coming years. So the last topic I'm going to talk about are outbursts from massive stars, which I'll cover very quickly. But again, I just want to pause and see if there are any questions on this bit. Okay, well, yeah.
I was just going to ask, like, so something like the Crab Pulsar, which spins at 33 milliseconds right now, and I think it was born with probably about 20 milliseconds. Does that fit in with the theory here or no?
Yeah, so Crab is what people think of as a typical pulsar. That one is actually born faster than most pulsars, we think. So it's a little bit faster than average. And yeah, it is a bit faster than the simple models I showed you before. So I think there's a good chance that something else is complicating the picture. And actually what I think is most likely is that there are stochastic processes that happen either at the end of the star's life or during the supernova explosion itself that can take a core, and even if it had no angular momentum to start with, it basically gets kicked and gets a little bit of angular momentum from that process. So people doing simulations of supernovae see this happen in their simulations, where even though they start the simulation with no angular momentum, the explosion develops in an asymmetric way, and so the material that's ejected during the supernova carries off a little bit of angular momentum, and that means the neutron star is left with a little bit of angular momentum in the opposite direction, and that's sort of a stochastic or random process. But they see their neutron stars get spun up to periods of tens of milliseconds or even faster in some of those simulations. So I suspect that's what's happening for many neutron stars and possibly the Crab Pulsar.
Okay, thanks.
Yeah. I've also worked on a similar process that happens at the end of the massive star's life during silicon burning, where gravity waves can actually carry angular momentum in a similar way. They can basically stochastically change the spin of the core of the star. And that may be important in some cases as well. So that's what I suspect. In that case, it also predicts that the rotation axis of the neutron star is basically random. And that is actually what we see for the double pulsar, is that the second born pulsar, it looks like its rotation axis is not aligned with the orbit. So that may be what's happening. Okay, so I'll briefly cover the last topic, which is what happens when gravity waves actually affect the evolution of the star. So they're not just carrying information here, they're also carrying energy. And that energy in some cases can be a lot, and it can actually really change what a star looks like, and it can also change what the supernova of a star looks like. And so we actually have a lot of evidence that massive stars, at the very end of their lives, they're doing something weird that's not predicted by standard stellar evolution models. And part of the reason we see this is that this is an example of one supernova observed by ZTF here at Caltech. This is a paper by Anna Ho. where this is the supernova light curve. And what they saw is this supernova brightened extremely rapidly. And basically the only way to explain this is if the exploding star immediately ran into a whole bunch of material surrounding the star called circumstellar material. And that converts some of the explosion energy into photons, which then make the supernova get very bright. So that's almost certainly what was happening with this event, and there's many others like this. And in this case, they were able to actually detect this star before it went supernova, or this probably wasn't the star, this is actually probably an outburst from the star that in this case happened about 2 weeks before explosion. So there have been other cases where we've seen those outbursts directly. And what's interesting is that stellar evolution models don't predict, in most cases, any major changes, any outbursts at the very end of a star's life. But those models don't include energy transport by waves. So again, what we think happens is that you have this very vigorous convection that's happening due to things like oxygen burning and silicon burning at the end of a massive star's life. And that puts a lot of energy into waves. So to order of magnitude, the amount of energy that you put into waves is something like the Mach number of the convection divided by the luminosity carried by that convection. And at the end of a massive star's life, the luminosity carried by the convection in the core, it can be enormous. It can be something like 10 to the 10 solar luminosities. So that's actually brighter than a supernova. Now, most of that energy doesn't make it to the surface of the star, but some of it gets put into waves. And so the waves can carry something like 10 to the 8 or 10 to the 7 L sun. And this is only happening sort of during neon and oxygen burning or silicon burning in the last year or so of the star's life. That's when you get these enormous wave powers. This translates to wave energies of order 10 to the 47 or 10 to the 48 ergs. So that's enough energy to basically, first of all, make the star much brighter, and second of all, eject a bunch of mass from the surface of the star, if that power can be transported to the outer layers of the star. And so I think what happens is in many cases, waves are able to transport quite a bit of energy to the surface. So the picture is that you have this very vigorous convection in the core of the star that excites gravity waves. Those then couple with acoustic waves that go out into the surface layers of the star, deposit that energy, and eject some mass from the surface of the star. So it's similar to what we saw for red giants, where you had convection at the outer layers, exciting waves that go into the star. In this case, we're thinking about convection in the core of the star that excites waves and then go to the outer layers of the star. So I'm going to go through this pretty quickly, but we've done some very detailed modeling at this point. It's quite complicated, so I'd say there's still a lot of uncertainties here, especially with the spectrum of waves that's excited by convection. But we can try to estimate from these stellar models basically how much power goes into waves and how much of that power actually escapes to the surface layers of the star where it can drive an outburst. So I want you to focus in this plot. This is one such model, including energy transport by waves, where the blue dashed line is showing you the amount of power that's actually escaping from the core as waves that's then damping in the surface layers of the star. And it's basically nothing until the last couple of years of the star's life, and then it can be of order 10 to the 6 or 10 to the 7 L sun. So that can be 10 or 100 times more energy than the photons are carrying at the surface layers of the star. So that means these waves can have a really profound impact. And in these models, what happens is it makes the star brighten by a factor of several. This is its path through the Hertzsprung-Russell diagram, which looks like a piece of abstract art, but I don't want to, stake my scientific reputation on this being true. But basically, the idea is that in many cases, the waves can power an outburst that makes the star go up into this upper right part of the diagram where it becomes much brighter. And that's only in the last couple of years or even less of the star's life. And the mass loss rates, according to these calculations, can be of order 10 to the minus 2 or 10 to the minus 1 solar masses per year. And for reference, that's probably more than a factor of 1,000 larger than the normal mass loss rates of these stars. So the idea here is that these waves in the final months or so of the star's life go to the surface layers of the star and eject mass at this extremely rapid rate. And that creates this very dense circumstellar material around the star. And the star only has maybe a few months to live at this point. So that material doesn't make it very far before the core of the star actually collapses and you get the supernova. So that material is still hanging around when the star explodes. And that means the supernova ejecta runs into that material and creates a very bright supernova. So we're seeing more and more of these events. There are lots of complications. But I just want to highlight some work by my student Samantha, who's been looking at this process in many different types of stars. And what we find is there's a couple types of stars where these outbursts are likely to be most important. So in most stars, which are these ones, there's probably not enough energy transported for this to be very important. There's a few cases in the upper part of this diagram where the waves probably do power an outburst. And one is actually at this very low mass here, means about 11 solar masses. And in those stars, the neon actually ignites degenerately at the end of a massive star's life. And that actually translates into more wave energy getting to the surface of the star. So we think actually the kind of the low mass supernova progenitors, about 10 solar masses, are more likely to have outbursts. And also potentially the higher mass supernova progenitors, more like 40 or 50 solar masses. And in these cases, what's happening is we actually see mergers between helium convective shells and carbon convective shells. That creates an enormous amount of power, and so that helps fuel outbursts as well. But we're still doing more work to figure out exactly which stars will have these outbursts and which won't, because the data also shows that a lot of supernova don't seem to be exhibiting this effect. And the last thing I'll mention is that my postdoc Xing-Chi has been modeling some events. So this is actually the same supernova that I showed you earlier, observed by ZTF, where you can get a very nice match to the data. So this is a light curve of this supernova if you just add a little bit of circumstellar material around the star. So in this case, we need maybe a few tenths of a solar mass of material. And the question is, what is creating that circumstellar material? And in this particular event, actually, we think this is actually probably more mass than can be ejected by the wave power in this particular event. So there are probably actually multiple mechanisms that can cause stars to eject mass at the end of their lives. The waves are only one of those mechanisms. The other mechanism that we think is really important for this event is called pulsational pair instability. So that's our favorite explanation for this particular event. That can also eject about this amount of mass at about the right time scale before explosion. So there's probably multiple things going on. Fortunately, these transient surveys are finding oodles of supernova that help us test these theories. So it's going to be fun to see how things develop over the next several years. So a lot of theory work needs to be done as well. There's still a lot of uncertainties in the fluid dynamics, but that's something that my group is working on. So hopefully I can give you an update. But I've run out of time, so I will just leave up some conclusions and take questions. Thank you, everybody.
Thank you, Jim, for an excellent talk, very instructional for all of us. Are there any questions for Jim? If you have a question, Bruce, go ahead.
Thanks for your talk, Jim. I had lots of questions during your talk, but the one at the end I want to focus in on. You talked about how waves are generated by convection. I wonder if you can get into a bit more detail of how you work out what is the fraction of energy in the convection that gets converted into waves and what the spectrum of those waves are.
Yeah, so that is not fully understood, I'd say. The basic idea is that, well, one way you can think of it is that you have gravity waves and they penetrate into the convective zone, but only a short distance. So if you think about convective motion sort of wiggling the tail of a gravity wave, that then translates to a wave that gets excited and goes out of the convection zone. And so the amplitude of that wave is basically going to be determined by how fast you're wiggling the tail.
Yeah, that was
And
what
that's-
Daniel Lacournay wrote in his paper. I guess it really comes down to what the buoyancy frequency is compared to, say, the frequency of the convective motions.
That's exactly right.
Say, if you actually have convective eddies that are pushing into the stratifier substantially, acting as kind of a topographic forcing.
That's exactly right. So that's kind of the other way to visualize it, is that you have convective plumes. They go up, they hit this boundary that's stably stratified, and that basically excites a wave that then propagates outwards. Yeah, so both of those processes are happening. And you're right that I think the main dimensionless parameter that's important is basically the convective turnover frequency relative to the buoyancy frequency in the radiative zone. And that's approximately the fraction of power that escapes, we think. That I said is the Mach number. It turns out that's basically that same ratio to order of magnitude. But the details,
no, that's great. If I can also ask another quick question, and when you're looking at the waves then propagating outwards, you must have included the inelastic effect. Is there any possibility that you have the waves overturning because they get to such large amplitude before getting to the outer shell?
Yep, absolutely. So one of the things I skipped over a bit is that, yes, in many cases, the waves get to very nonlinear amplitudes, and that will cause overturning of the stratification, and that will damp a lot of the wave power before it gets out of the star. So we are trying to account for that in our models now. Basically, when the waves become nonlinear, like in this case, we basically suppress their power until they become linear again. But nonlinear wave breaking is a very complicated process that's hard to calculate analytically. So I think that's one of the major sources of uncertainty, is how much do these nonlinear effects really damp the waves before they get out?
No, I fully agree with you. Thanks.
Yep, thank you.
More questions for Jim? So I have another question about when you were showing the spin evolution of massive stars, you had the main sequence and then a very sharp drop. And that was that the angular momentum of the core alone, or?
Yeah. So in this case, what I'm plotting is basically the specific angular momentum of material in the helium core. So I think it's basically just the helium core angular momentum divided by its mass. And
okay. So what I was wondering is that you are transferring all this angular momentum very quickly on, I don't know, stellar timescales, right, to the envelope. And so does it have any dynamical effect? Like you have more mass loss, for example, or is just a tiny fraction of the envelope angular momentum such that delta J over J is just, I don't know, like less than 1%?
Yeah, that's a fantastic question. It turns out, so when the star becomes a red supergiant, basically its moment of inertia becomes so big that even if you put all the angular momentum from the core of the star into the envelope, it doesn't spin up the envelope appreciably. But it turns out when the star first moves off the main sequence, it doesn't have a big convective envelope, and its outer layers, actually, even though they grow to large radius, they still have a really tiny amount of mass. And so they actually have a fairly small moment of inertia. So it turns out in that case, you actually can inject some angular momentum to the surface, and that can potentially cause the star to start rotating faster than its breakup velocity at the surface in some cases. And so I actually had a paper last year that I didn't talk about where we showed that in some cases that can cause stars to lose mass right when they're evolving off the main sequence. And this could be related to outbursts from stars like luminous blue variables. So we think this is one mechanism that stars can lose mass, but it's only, it's right in this phase, right when they evolve off the main sequence.
And I guess you would need to have observations of a sample of stuff around that evolutionary phase.
So that is where luminous blue variables live, is basically right when this is happening. That is where those stars live in the HR diagram. So it's consistent in that sense with this hypothesis. But I don't think it can explain all of the LBV outbursts, maybe some of them.
I see. Okay, thanks. Any more questions for Jim? I have one more. Could you, like in a nutshell, explain why your effective viscosity is 2 powers less of omega over Brunt relative to Tyler's Sproit?
Yeah, so that power law, I think it could have worked out to just about any power law. The reason it works out to that one, I think, is that so basically what's important is how large of a magnetic field do you develop due to these motions, these instabilities. So in other words, we know the linear instability occurs, and that causes basically these non-radial, or the radial component of the magnetic field, to get excited. But how large of a magnetic field you develop depends on how large the amplitude of the instability grows to. So that depends on the nonlinear damping processes. And we think that those damping processes are actually weaker than what Sproit posited. And the reason they're weaker, we think, is that he was basically assuming that the energy in the background toroidal magnetic field gets damped out, but we think it's just the energy basically in the perturbed magnetic field. The background magnetic field is it's basically, to first order, it's just a uniform toroidal field. There's no small scale structure. So we think you can't really damp energy, the main energy of the field. You can only damp out the small scale field structures that develop as a result of the instability. So that translates to basically a smaller nonlinear energy dissipation rate, which translates to larger magnetic field strengths and larger viscosities. And it happens to be a different power law that's different by a factor of 2. But I don't think it has to be exactly a difference of a 2 in the power law. It could have worked out too.
Yeah, but that, I mean, just understanding the physics of why it's less efficient, that was clear. Thanks. Any more questions before we let people go here? Last chance. All right, but if not, then thank you very much, Jim, for such a nice talk. And yeah, I don't know if anybody else has any last minute thoughts or questions or ideas. We would definitely like to have you come visit. I mean, I know you like mountains too, so this is close to us, so it's a good opportunity. But in the meantime, we do what we can, right? So.
Yep. Well, thank you everybody for coming. It was a pleasure.
Thanks again for accepting to give this very nice talk. So I'll stop the recording now.